ecological threat we face: climate change. As our planet heats up, some parts of the world become too dry for human life or for growing food. Others are battered by more floods and storms. Some places suffer both tragedies. I now understand that the climate crisis is actually a crisis of water, at least in how it affects people's lives. We can't solve our water crisis without also dealing with the climate crisis. But as things stand, we aren't moving anywhere near quickly enough. Right now, I'm standing on a small shingle beach at the mouth of the River Thames in England. Over my shoulder, I can see the hulking silhouette of the Grain Island power plant. It's still burning fossil fuels, and so are more than 80 other power stations in the UK alone. In front of me is the North Sea, and way out there under the waves, oil and gas exploration is still happening, a pattern that's repeated around the world. We need to act, but what can we do? What's clear is that fixing our relationship with water means tackling the climate crisis. These are daunting problems, but in this final episode, we'll find out how water itself could offer crucial solutions. We'll hear about ideas that tap into the unique and weird chemistry of every water molecule on the planet, from the steamy mist in the warmest rainforest to the freezing cold sea here at my feet. Nuclear fusion is one of these possible solutions. This is a way of producing practically unlimited clean power. We just need to sort out a few extremely difficult engineering challenges. And as we'll soon hear, water plays a vital role. Physicist Dr. Fernanda Ramini runs some of the largest nuclear fusion experiments in the world. This sounds crazy when you say it out loud, but she and her colleagues at the Culham Centre for Fusion Energy are essentially trying to create an artificial star in the quiet English countryside.
Fusion is what happens in the stars. So basically fusion is what gives energy to all of us because it's what happens in the sun.
At the moment, when we say nuclear power, we're almost always thinking about nuclear fission. This is what the current nuclear power stations use, and fission is all about breaking heavy elements apart.
You take a big element and you split it, and that releases some energy.
Nuclear fusion, the technology Fernanda works on, is the opposite.
We take some very light elements and we fuse them together, and that releases energy.
So in your case, you take very small atoms, force them together, and then release energy that way.
Yes.
So that sounds simple enough.
Yes, it sounds simple enough. There are a couple of problems. First of all, that you need very high temperatures. So that's why we need to use what is called the plasma, which is a gas, and we heat them to temperatures high enough where this fusion effect can happen.
Give me some numbers. What kind of temperatures? How difficult is this challenge?
So in the sun, you have temperatures of about 15 million degrees. On Earth, because we...
15 million degrees
15
Celsius.
Million degrees
This
Celsius.
is in the centre of the sun.
This is around the sun. On Earth, because we are dealing with something that has much less density, the temperatures need to be much higher. So we are talking about temperatures about 150 million degrees in our machines.
So 10 times hotter than the centre of the sun.
10 times hotter than the sun.
This is a huge challenge. Without the massive gravity at the centre of the sun forcing the atoms together, on Earth we need 10 times the temperature to get fusion reactions started. To reach those temperatures, Fernanda and her team heat the cloud of plasma, the superheated gas, using technology that's actually quite similar to a microwave oven. But this is no normal microwave. These are temperatures hot enough to instantly vaporize any material in the universe. I asked Fernanda just how you go about safely confining a cloud of plasma heated to 150 million degrees Celsius.
To do that, we use very powerful magnetic fields because these are charged particles, so they stay around the magnetic fields.
The plasma is held, actually suspended in the air, by these extremely powerful magnetic fields. What sort of machine can do such futuristic things? The one Fernanda works with is a design called the tokamak.
The machine is a big metal donut, about 3 meters in radius and about 4 meters tall. The inside is where we keep this gas at 150 million degrees. It's not only very hot, but it also produces radiation. So the inside walls of this donut can get very hot, can get to temperature of 1,000 degrees.
This is some of the most challenging engineering anywhere on the planet. Fernanda's team work on the Joint European Torus experiment. They and others around the world have put decades into making the physics of fusion actually work in practice. And that's because the rewards could be so huge. Fusion has the potential to provide practically limitless supplies of clean energy. How? Well, it's partly down to the fuel, which comes from water.
A fusion power plant, the first generation that we think we will develop, will use what is called a deuterium-tritium reactions.
Deuterium and tritium are slightly heavier forms of hydrogen. Together, they make up the fuel needed for fusion power.
It turns out that deuterium is very common in water.
And so this is just naturally occurring?
It's just natural. It's not radioactive or anything. So you can extract the fuel for a reactor from water.
I mean, is it too much to say that given the amount of water on Earth and given the amount of deuterium that is in there, that this is essentially a limitless fuel?
The deuterium is limitless. Deuterium is only half of the equation, but the second part of the fuel will be generated within the power plant itself.
It's really extraordinary to me that in the course of the programs we've seen how harnessing water has been so important at every stage of human development, whether it's agriculture or manufacturing or whatever else. It's really important. And now we're really delving into the chemistry of it to potentially power the future.
Yeah, it will not only power the power plant as fuel, it will also produce electricity. You will do it in the same way that the Victorians did, or in the same way as most power plants do it now. The fusion will heat up water to temperatures where it becomes steam, and the steam will turn turbines, and the turbines will generate electricity. So the water will be on both sides. It will be the beginning of the reactions, but it will also be the part that produces the electricity.
Billions of years ago, the basic chemistry of water allowed all life on Earth to evolve. Today, it may hold the key to powering our future. Even the few waste products of fusion reactions are far less dangerous and much easier to deal with than the waste from current nuclear power plants. It seems almost too good to be true. Of course, as Fernanda says, there are all kinds of challenges in scaling this technology up for use in a full-sized nuclear fusion power plant. But talking to people like her, I can't help feeling that we will get there eventually. The question is, will we get there in time to avert some of the water-related ecological catastrophes explored in this series? Most importantly, could it help avert the climate crisis?
We are seeing the impacts of climate change now play out in real time. They're no longer subtle.
And let's be very clear about this.
The collapse of our societies.
Certainly, addressing that challenge will also need massive scaling up of renewable energy like wind and solar power. A wide mix of clean energy will be required if we want to reduce our reliance on fossil fuels and cut the world's carbon dioxide emissions. We'll need better ways of storing clean power once we've produced it. And we'll also need to develop ways to actively take out the carbon dioxide that's already in our atmosphere. But yet again, the natural properties of water itself offer a potential solution. To understand how, first we need to talk about photosynthesis, the single most important biological process on Earth. It relies on
to transform water and carbon dioxide into sugar, which is the substance that stores all that energy.
That's Professor Fernando Romo, a chemist at the University of Central Florida.
It's super important. The way plants grow, they need energy to grow. And the only way plants figure that out is by harvesting that light from the sun. So without photosynthesis, there will not be plants. And without plants, there will not be life on Earth.
The first step in this life-sustaining process is all to do with water.
What the plant does first is traps the light that comes from the sun, and with this light it just rips apart the molecule of water. It removes electrons and removes protons, and it just produces oxygen, right? And that goes away. That's actually the waste of the photosynthesis. And the process is called water splitting, because the plant is literally splitting the water apart.
So water is providing the ingredients for plants to photosynthesize, and that's how they create fuel for themselves, and also every than that.
Yeah, definitely. Over the millions of years, all the plants that being created, they get trapped under layers of sediment, and over the millions of years, all that matter transforms into the fossil fuels.
The ancient sunlight trapped in ancient plants would be fine if it all stayed under the ground. But here's the problem. Humans have developed ingenious ways to find and then burn all these fossil fuels. This releases the energy stored in them, but also releases carbon dioxide into the air. There just aren't enough living plants in the entire world to recapture all that carbon dioxide and rebalance the atmosphere. The excess carbon dioxide ends up warming the planet, and that, as we've seen in this series, is one of the main causes of the global water crisis. This is where scientists like Fernando come in. His solutions take inspiration from the ways plants work, but also look for ways to improve things, because photosynthesis is not as efficient as it could be.
A natural plant will have an efficiency to store energy at about 2%. So of all the energy that the plant takes from the sun, only about 2% is actually stored. The other 98% is consumed in order to make the plant grow. So in the case of artificial photosynthesis, we want to recreate this very same process, but utilizing artificial materials in which we are not limited by natural selection.
Fernando and other researchers are essentially trying to hack the process of photosynthesis, using artificial materials and chemicals to convert much more of the sun's energy into fuel than plants can. And even in most of these new, high-tech forms of artificial photosynthesis, one crucial thing remains the same.
The bottom line is that water is the first step in the photosynthesis.
Artificial photosynthesis has huge potential for providing clean energy, and also for capturing carbon dioxide, that's CO2, from the air.
It will be sort of like adding an extra technology besides plants, right? Because plants can naturally remove the CO2 from the air, but right now there is not enough plants in the world for that. So a technology like this can definitely contribute to reduce the effects of global warming and perhaps fix it in the long run.
I love this idea that humans can learn from the way plants use water and improve the very process that powers life in the first place. As usual, there are all sorts of technological challenges before something like this can be rolled out on a global scale. And of course, halting the destruction of existing natural plant life is a vital part of that too. But it's encouraging to know that this research is making rapid progress. Taking a step back, it's fascinating to me that fusion and many forms of artificial photosynthesis both rely on water. The same substance whose misuse is at the heart of many of our biggest environmental concerns, droughts, floods, pollution, may also offer some powerful solutions. But before I get too carried away, I need to return to water historian and geographer Terje Tvedt, who we met way back in the first episode of this series. I float the idea that we might be on the brink of truly harnessing the full power of water with our new technology.